We've just done an experiment where we have looked at making an electrochemical cell. We've had a half cell made from zinc and zinc sulfate, zinc chloride, and we've had a half cell made of copper and copper sulfate. So I'm just going to fix that one there. So I've got the wrong thing down. And we're able to use a voltmeter to see what voltage or EMF, electromotive force, that cell could make. And it was hard to make any observations, but what we did notice is that the zinc ones were quite thin at the bottom, as if they've been eaten away, and the copper at the bottom looked really pure, looked really clean, as if it's been added onto. If we left it running for long enough, your copper sulfate would probably fade in colour a bit, and you would start seeing the zinc completely eat away. Right? So this is how an electrochemical cell works. This is a simplified picture of it. I'm not going to use the word diagram for that because a cell diagram is slightly different, and I'll show you that towards the end of this video. Before I get into that though, I want to go through the background for it, and that you've probably done things called displacement reactions before, where we look at the reactivity of metals by seeing which ones react in solutions of the ions of the other ones. The more reactive ones, so the ones higher up the activity series, will react with ones that are considered less reactive. So zinc, when I put it in copper sulfate, tends to react. And we have observed this in other years of chemistry and science. The colour of the blue copper sulfate will fade a little bit, and you'll see copper deposits on the zinc. What you don't notice, because it's hard to see, is that the zinc is actually smaller than it was. You might have also done it with magnesium and copper sulfate and so on, anything that is higher up the activity series than copper. If you go the other way around though, you get no reaction. If I put copper and zinc sulfate, there's no observable reaction. Nothing happens. And that's because, in our old way of thinking of it, zinc is a more reactive metal than copper, or higher up the activity series. The activity series is really important for where we're headed with this, but we're going to use things called standard electrode potentials to justify the activity series of metals, for example. That's coming next week. This reaction here, we can use a whole lot of words to describe it. Because you've got a reaction, we can use half equations, combine them to make an overall equation, to show that it is oxidation and reduction, the oxidation of zinc, the reduction of copper too. We can say it's spontaneous because it occurs without us having to provide electricity or energy. What you're going to learn is that it's got a positive electromotive force, or what we're going to use when we talk about cells, standard electrode potential for the cell is positive, which is why it's spontaneous. This means that this reaction could be used to make a cell, and that's what we did in our experiment. So I'm going to go through that with you now and how we summarise this so we don't have to draw something like this every time, but also to show you what's happening in it. Our cell was made up of two electrodes, or two half cells, which have an electrode in each of them, and those electrons are sitting in a solution of the ion of that substance. So our copper electrode was sitting in a copper 2+ solution. Our zinc electrode was sitting in a solution of zinc ions, in this case zinc chloride. Those cells were connected by a wire through a voltmeter. Well, actually that's actually only going to measure our potential. It isn't really going to make the cell run that well because a voltmeter is connected in parallel. Alright, we could have put a lamp in there if this gave us enough voltage and enough current to power a lamp. It gave us enough voltage, by the way, just not enough current, so not enough power. And this thing in the middle here was a bit of filter paper soaked in potassium nitrate called a salt bridge. The reason we use potassium nitrate is because those two ions, potassium, so K+, and nitrate, NO3-, are quite motile. They can move very easily. This actually completes the circuit. This completes our circuit to allow it to run. Without the wire, nothing will be observed. Without the salt bridge, nothing will be observed. And we did see that. Before the salt bridge, the voltage on here should have been 0. After the salt bridge, we got up to about 1.3 volts, I think, for some of you. All right, so there's enough voltage to power a small lamp. Problem is there's not much current. Okay, so what's happening in there? Well, just like when we put zinc in copper sulfate, you've got oxidation and reduction happening. The zinc is being oxidized to become zinc 2+. So over here, I've got the same half equation as over here, which is oxidation. Because it's oxidation, which starts with a vowel, I know that that piece of zinc must be the anode. It's called the anode. However, in this case, the anode is going to be negatively charged. Remember in electrolysis it was positively charged? If it's giving off electrons, repelling electrons, it must have a negative charge. So this is actually the negative terminal of our battery or cell. So it's actually negative. But notice that our rule, the vowels stay together. Okay, so in a cell or a battery, the anode is the negative terminal. That's why we often plug the black coloured lead into it and so on in a battery or a power pack or whatever. Over here, we've got the opposite happening. Same as this one here, we've got copper depositing, and actually the colour of this would fade. So it's going from copper 2+ to copper metal. This is the addition of electrons, so it's reduction. And this means that the copper must be the cathode. And in this case, it's going to be the positive terminal of our cell. So what else do we need to know? We need to know which way the electrons are flowing. And I've shown that here. If this is releasing electrons, they've got to go somewhere. And the only thing present here that can carry electrons away is a wire. So our copper wire here, it doesn't matter what it's made of as long as it's a conductor, our copper wire here allows for the flow of electrons. And so whenever you draw these and you're asked to show the flow of electrons, it's always from anode to cathode, even if you accidentally put the anode on the right hand side. Okay? So anode to cathode. The potassium nitrate, or whatever the salt bridge has been soaked in, has to be ionic, because those ions are going to flow to where they are needed to balance the charge out. If electrons are leaving this half cell, to keep it electrically neutral, the negative part of the potassium nitrate, the anion, must flow into this solution. So there's more and more zinc ions in here, but there's also going to be nitrate ions going into there as well. So that we've got in here zinc chloride and zinc nitrate. We've got a mixture of the two after the cell's been operating for a while. Over here, conversely, you've got copper 2+ becoming copper, so you've got an excess of sulfate ions. So the potassium ions go in there to balance out that charge. So we've got copper sulfate and potassium sulfate in there after the cell's been operating for a while. Now the last thing I need to show you is how to write this, because drawing one of those all the time takes forever. The convention is that the anode goes on the left when we draw what's called a cell diagram. So the way that I like to say is that it's as easy as A, B, C. So what we're going to do is we're going to draw our anode half cell first. States of matter are important here. Your anode must be a solid. And when we do ones that have got two solutions reacting, like Fe2+ and Fe3+, I'll show you how to do those when we meet those. I'm just going to stick with a simple half cell now. So our anode is the zinc. So I write zinc with a little s there. That zinc has a physical barrier between itself and the zinc chloride. Now the chloride's not important, it's a spectator ion, it's not involved in my half equation, so I don't need to say the chloride bit. What I do need though is the zinc 2+. Because there is a phase change, this is a solid, this is a solution or liquid, then I use a backslash to show that there is a state change here. I also use the subscripts but I need that line as well. And I write Zn2 plus aqueous. The reason I need to say it's aqueous is that could be a gas. It could be a pure liquid. We're not sure. So by saying aqueous, we're specifying which different phase it is or state. The B is for the salt bridge. The bridge is represented simply by a double backslash. Okay, this is our salt bridge. You don't need to say what's in it because it could change. It actually doesn't matter what's in there so long as they're motile ions, ions that can move. Then we come across to here and we actually do the solution first for our reduction half cell. So we do our Cu2 plus, which is aqueous. There's a state change from aqueous or liquid to solid. So I do my backslash again and put in my C, cathode. And in this case it's copper. This is what we call a cell diagram for this particular cell. Anode, and then what it's sitting in. Bridge, B. The next solution, and then the cathode. So A, B, C. Alright, so nice easy way to try to remember that. If you draw it the other way around, it will not be spontaneous, because you're saying the anode would be the copper one. And that can't undergo oxidation unless you were to put electricity into it, and that's called electrolysis. So that would be the reverse of this. So it has to be oxidation, bridge, reduction. Anode, bridge, cathode. However you want to remember that. As I say, when you do have two solutions, for example, permanganate and manganese 2, for example, iron 2 plus and iron 3 plus, you're going to have a different electrode, probably carbon, because carbon's quite unreactive. So you'd put the 2 in the middle there. And because they're both in solution, you separate them just with a comma. So for the one I've just described, I'll just write it up the top, you'd have, if it was the oxidation reaction, for example, it'd be carbon would be your anode, and then Fe2 plus aqueous, Fe3 plus aqueous. Then you'd have your salt bridge and whatever it was reacting with. Okay, the rest of it. So the other half cell. So you use a comma to separate things that are in the same phase. Now gas dissolved in a liquid is the same phase. So if you had hydrogen gas and hydrogen ions from an acid, then you'd use a comma because they are considered the same phase. They're both fluids, so they can both flow. And that, in a nutshell, is electrochemical cells. We'll get into EMF next week and how we do that and how we predict if a reaction is going to be spontaneous or not. And we'll get more and more practice in writing these next week as well. But they are our two main skills to be able to do there.